Good evening. My name is Shrikant Srinivasan, and I am going to be giving a small lecture on flip-flops. So, I am studying in mechanical, second year mechanical engineering, and my registration number is 16BME 1133. I promise that this PowerPoint presentation is made entirely by me, and this video. So, I'd like to give a small introduction on a bistable multivibrator. So, what is a bistable multivibrator? In the bistable multivibrator, both resistive and capacitive networks C1R2 and C2R3 in figure 1. As you can see in the figure, R1, R3 and R2, R4 are resistors, whereas the Q1 and Q2 are transistors, and the red and blue junctions, they are switches connected with black lines. So in the bistable multivibrator, both resistive and capacitive networks C1R2 and C2R3 in figure 1 are replaced by resistive networks, just resistors or direct coupling. This latch circuit is similar to an astable multivibrator, except that there is no charge or discharge time due to the absence of capacitors. Hence, when the circuit is switched on, if Q1 is on, its collector is at 0 volt. As a result, Q2 gets switched off. This results in more than half of positive volts being applied to R4, causing current into the base of Q1, thus keeping it on. Thus, the circuit remains stable in a single state continuously. So, similarly, Q2 remains on continuously if it happens to get switched on first. Switching off state can be done via set and reset terminals connected to the bases. For example, if Q2 is on and set is grounded momentarily, this switches Q2 off and makes Q1 on. Thus, set is used to set Q1 on and reset is used to reset it to off state. So in this diagram, set is used to turn on Q1 and reset is used to turn off Q1. When one switch is open, when Q2 is on continuously, it happens to get switched on first. Switching of state can be done via set and reset terminals. If Q2 is on and set is grounded momentarily, this switches Q2 off. So next we move on to flip-flop, and I would like to give a small introduction on what is a flip-flop. What is a flip-flop? In electronics, a flip-flop or latch is a circuit that has two stable states and can be used to store state information. A flip-flop essentially is basically a bistable multivibrator. The circuit can be made to change state by signals applied to one or more control inputs and will have one or two outputs. It is the basic storage element in sequential logic. As we all have studied logic gates, this flip-flop is one of the most basic storage element in sequential logic. Flip-flops and latches are fundamental building blocks of digital electronic systems used in computers, communications, and many other types of systems. Whereas gates are fundamental, a combination of gates can be used to make flip-flops, which are in turn the building blocks of digital electronic systems and in computers, basically in all sorts of electronic devices. So this is an image and the truth table of a JK flip-flop. When the terminals J, K and Q are given 0, the output is going to be 0. And when J and K are off but Q is on, output is going to be 1. Similarly, when J is 0 and K is 1 and Q is 0, the output is going to be 0. When J is 0, K is 1 and Q is 1, the output is going to be 0. So this characteristic equation is given by output equals J Q dash plus K dash Q. Flip-flops. Flip-flops and latches are used as data storage elements, which we already saw in the previous slide that most of the flip-flops are used for storage and communication systems. A flip-flop stores a single bit binary digit of data. One of its two states represents a 1 and the other represents a 0. So it can exist in two states. One state is the on state and the other state is off state. Or basically, one state is 1 and the on state is 1 and the off state is 0. Such data storage can be used for storage of state, and such a circuit is described as sequential logic. When used in a finite state machine, The output and next state depend not only on its current input but also on its current state, and hence previous inputs. It can also be used for counting of pulses and for synchronizing variably timed input signals to some reference timing signal. Flip-flops can either be simple, transparent or opaque, or clocked, synchronous or edge-triggered. We are going to be, in this presentation, we are going to be seeing lots of different types of flip-flops, positive edge-triggered, negative edge-triggered, etc. Although the term flip-flop has historically referred generically to both simple and clock circuits, in modern usage, it is common to reserve the term flip-flop exclusively for discussing clock circuits. The simple ones are commonly called latches. There are many different types of flip-flop circuits. There are latch circuits, there are gated circuits, and there are clock circuits. Using this terminology, a latch is level sensitive, whereas a flip-flop is edge sensitive. That is, when a latch is enabled, it becomes transparent, while a flip-flop's output only changes on a single type, positive going or negative going of clock edge. History of flip-flops. So flip-flops were not a recent invention. They were invented very long back, and that's what led to more inventions and innovations in the field of electronic engineering. The first electronic flip-flop was invented in 1918 by the British physicist William Eccles and F.W. Jordan. It was initially called the Eccles-Jordan trigger circuit and consisted of two active elements. They were basically comprised of vacuum tubes. The design was used in the 1943 British Colossus code-breaking computer, and such circuits and their transistorized versions were common in computers even after the introduction of integrated circuits. As I told, these flip-flop circuits that were first discovered, they led to more complicated circuits in computers, and basically very first computers had flip-flops for communication. Were common in computers even after the introduction of integrated circuits, though flip-flops made from logic gates are also common now. Early flip-flops were known variously as trigger circuits or multivibrators. These were because they were made from transistors and not just gates. Implementation of flip-flops. Flip-flops can either be simple, transparent, or asynchronous, or clocked, synchronous. The simple ones are commonly described as latches, while the clock ones are described as flip-flops. So flip-flops can basically be classified into many types. Under simple you get transparent and asynchronous, and under clock you get synchronous. And in the simple ones, most commonly called latches, while the clock ones are flip-flops. Single flip-flops can be built around a single pair of cross-coupled inverting elements. Vacuum tubes, bipolar transistors, field effect transistors, inverters, and inverting logic gates have all been used in practical circuits. So these simple flip-flops, they can be built very easily, most common, and the vacuum tubes, bipolar transistors are mostly used for making simple flip-flops. Inverting logic gates have all been used in practical circuits, and such flip-flops made from simple items, they are used in all practical circuits. Implementation. Clock devices are specially designed for synchronous systems. Such devices ignore their inputs except at the transition of a dedicated clock signal, known as clocking, pulsing, or strobing. Clocking causes the flip-flop either to change or to retain its output signal based upon the values of the input signals at the transition. Some flip-flops change output on the rising edge of the clock, others on the falling edge. So some flip-flops, their output remains the same irrespective of the output, except for the transition of a dedicated clock signal, and this is known as clocking or pulsing. So basically, clocking causes the flip-flop to change or retain its output signal based upon the values of the inputs. Since the elementary amplifying stages are inverting, two stages can be connected in succession as a cascade to form the needed non-inverting amplifier. In this configuration, each amplifier may be considered as an active inverting feedback network for the other inverting amplifier. Thus, the two stages are connected in a non-inverting loop. Although the circuit diagram is usually drawn as a symmetric cross-coupled pair, both the drawings are initially introduced in the Eccles-Jordan pattern. So since Eccles Jordan, they were the first people to discover and make these invent these flip-flops. They created a patent for these, and the two stages are connected in succession to form the needed non-inverting amplifier. These two stages are connected in a non-inverting loop although the circuit diagram is usually drawn as a symmetric cross-coupled pair. And these two are the flip-flop schematics from the Eccles and Jordan patent filed in 1918, which is exactly a century back. One drawn as a cascade of amplifiers with a positive feedback, and the other as a symmetric cross-coupled pair. As we can see, the first one is a cascade of amplifiers with positive feedback, and the second is a symmetric cross-coupled pair. So flip-flops, like I said, flip-flops come in many types, and they can be divided into some common types: the SR, set reset, D, data or delay, T, toggle, and JK. The behavior of a particular type can be described by what is termed the characteristic equation, which derives the next, that is after the next clock pulse output, Q next in terms of the input signals and the current output. So this is a simple flip-flop circuit, a traditional simple flip-flop circuit based on bipolar junction transistors. So as we can see, A1 is connected to a transistor and A2 is also connected to the transistor, and these are connected to voltage sources, and the circuit as a whole is a simple flip-flop circuit. We come to the first type of flip-flops, the SR NOR latch. When using static gates as building blocks, the most fundamental latch is the simple SR latch. This is the most fundamental of the flip-flops, where S and R stand for set and reset. It can be constructed from a pair of cross-coupled NOR logic gates. The stored bit is present on the output marked Q. While the R and S inputs are both low, feedback maintains the Q and Q outputs in a constant state, with Q the complement of Q. If S set is pulsed high while R reset is held low, then the Q output is forced high and stays high when S returns to low. Similarly, if R is pulsed high while S is held low, then the Q output is forced low and stays low when R returns to low. So basically, when S is high and R is low, Q remains at high even after S is brought to low. Similarly, when R is high and S is low, even after S is brought to low, both Q remains in low. The R equal to S equal to 1 combination is called a restricted combination or a forbidden state because as both NOR gates then output zeros, it breaks the logical equation Q equals not Q. The combination is also inappropriate in circuits where both inputs may go low simultaneously, a transition from restricted to keep. The output would lock at either 1 or 0 depending on the propagation time relations between the gates, a race condition. So both R and S cannot be 1 because then both NOR outputs 0, and then it breaks the equation of the SR NOR latch, which is Q equals not Q. This combination is also inappropriate in circuits where both inputs may go low simultaneously because this is a restricted combination. Hence, the output would lock at either 1 or 0 depending on the propagation time relations. To overcome the restricted combination, one can add gates to the inputs that would convert SR equals 1 1 to one of the non-restricted components. That can be Q equals 1 1 0 referred to as an S dominated latch, Q equals 0 0 1 referred to as an R dominated latch. We saw that when S is high and R is low, the Q outputs high. So when Q equals 1 and 1 0, this is referred to as S dominated latch, and when Q is 0, it's referred to as an R dominated latch. This is done in nearly every programmable logic controller to avoid and overcome the restricted combination. Keep state 0 0 referred to as an E latch. The keep state 0 0 is called as an E latch. Alternatively, the restricted combination can be made to toggle the output. The result is the JK latch. So combining these outputs and inputs in different ways gives us different types of latches, as we will be seeing in the further slides. The characteristic equation is given as Q0 equals R0 Q plus R naught S plus or Q naught equals R naught Q plus S.